In this video, I'll talk about the rate of change of functions. The rate of change of a function is actually really important, especially when the function is changing with respect to time. For example, the rate at which energy in a system can change with time tells us how to move energy around in a system to accomplish a desired task. Lots of engineering problems are related to moving energy from one place to another in a system. The equations describing the rates at which energy can change are particularly important. Newton's second law, for example, governs the rate at which a body will accelerate when a force is applied to it. The equation is typically written as the sum of forces applied to the body equals the body's mass, m, times the body acceleration, a. Acceleration, however, is just a rate of change of velocity. A velocity change, delta v, divided by a corresponding change in time, delta t. This can be rearranged as the rate of change of velocity with time is equal to the applied force divided by the mass. Since a mass's velocity tells how much kinetic energy the mass has, this equation describes how the mass's energy changes with time. If we know how quickly we need to move something, this equation can tell us how much force we need to apply or how heavy to make the mass. Let's look at this equation in the special case when the force applied to the mass is constant. I've got a stationary mass m on rollers, and I'll apply a constant force to the mass rightward starting at time t equals 0. The variables a, v, and x are the acceleration, velocity, and position of the mass, and they're assumed to be positive to the right. Newton's third law says that the acceleration, or the change in velocity with time, will be f divided by m. Since f is constant, the acceleration will be constant and the velocity increases at a constant rate. Graphically, the acceleration and velocity look like this as a function of time. The acceleration is a constant and is the ratio of force to mass. The velocity increases at a constant rate, so it's a straight line with a slope of f divided by m. So at any point on the velocity curve, the rate of change of velocity with time will be the value of acceleration at the corresponding time. Now let's see what happens when the rate starts changing with time. We can see this by looking at the cart's position, or how far the cart's moved. We've already seen that for a constant force, the velocity increases at a constant rate. The velocity is the rate of change of position with time, so the value of velocity here will give the slope of the position curve. So at this time t1, the velocity is v1. That means that the slope of the position curve at time t1 will be v1. At a later time, t2, the velocity is higher, and the rate of change of the position curve will also be higher. The slope of the curve at time t2 is the value of the velocity v2 at that time. Likewise, at a later time t3, the velocity will be higher still. The velocity of the cart at any time is the slope of the line that's tangent to the position curve at that time. The cool thing about this approach is that the force applied to the cart could be any arbitrary function, rather than the simple constant force we used here. An example of a force that varies with time could be this oscillating sinusoidal signal. If we apply this force to the mass, this curve will then be the derivative of the mass's velocity. Here, the slope of the curve is 0. Here, the slope of the curve is its maximum positive value. Here, the slope of the curve is 0 again. And at this point, the slope of the curve is its maximum negative value. So the velocity curve will look something like this. In this video, we talked about why the slope of a curve that's a function of time can be important. In the next video, we'll talk about how to calculate the rate of change of an arbitrary function. This rate of change is called the derivative of the function, and the process of determining the derivative is called differentiation.